Welcome back. During this slide, I would like to give an overview to you about the typical signal shapes throughout the different coordinate transformations as part of the FOC algorithm. As you can see, for the first step, we are measuring the free phase currents of the motor. These measured phase currents in case of a PMSM can be described in a sinusoidal free phase current system. You may remember that we shall filter these measured phase currents in order to utilize the base harmonics of them, and afterwards the so-called Clark transformation can be applied to them. The latter mathematical operation transfers the measured three-phase current system to a two-phase coordinate system. I find it important to mention that within the Clark transformation, a stationary reference frame is being used for this mathematical operation, which means that our coordinate system, both the three phase and two phases, are stationaries and the physical quantities are changing compared to them. It is similar as you would sitting on a bridge and observe the cars passing below. From this point of view, the observer is in stationary state while the physical surroundings are constantly changing. The red arrow represents the theta measured electric rotor angle according to the applied encoder. We are going to use this angle information to perform the so-called Park transformation. This is going to be a mathematical operation as well, just like in case of our Clark transformation. But at this time, we are going to describe the measured phase currents in a rotating reference frame, which alternatively means that our two-phase direct quadrature coordinate system is going to rotate with the rotor of the PMSM machine. To mention the previous example, this scenario would mean that the observer is sitting in the car, which doesn't have a relative motion compared to the observer. In this rotating reference frame, the measured phase currents and other physical quantities such as fluxes and phase voltages can be observed as if they would be plain DC quantities. These coordinate transformations from AC to DC quantities are mandatory to ensure the sufficient working behavior of the PI regulators during the FOC algorithm. The PI current controllers are regulating the direct and quadrature current components to the appropriate requested value. The control signals are going to be the direct and quadrature voltages that shall transform back the three-phase voltage system by utilizing the inverse Clark and Park transformations. During the inverse Park transformation, we shall use the electric angle information from the PMSM rotor to appropriately describe the controlled direct and quadrature voltages in the XY stationary coordinate system. After we have utilized the controlled voltages in the XY plane, we shall transform these physical quantities further to the three-phase coordinate system. The so-called SVPWM algorithm is being used for the most efficient utilization of the available DC bus voltage to the PMSM motor phases. The function software that we are going to develop together is going to calculate the appropriate phase voltages that the so-called BSV or base software shall transfer to effective EGBT or MOSFET switching signals. After the three-phase voltages are being fed to the electric rotary machine, phase currents are going to flow that we are measuring in the next iteration of the FOC algorithm. As you may see, the upper mentioned steps are being repeated constantly with a certain time period. This is called the task time. The algorithm is manipulating the high phase currents according to the given input of the user. Within this slide, I would like to bring closer to you the practical implementations and working principles related to the FOC control algorithm development. We have seen that the first major step during the process of the algorithm is the current measurement. This is usually achieved by using a so-called shunt resistors that have a relatively small voltage drop when current passes through them that we are able to measure with a differential amplifier circuit. A gate driver circuit is being used as an intermediate hardware component between the EGBT or MOSFET bridge and the microcontroller. This component is mandatory to ensure the correct switching behavior of the semiconductors as part of the inverter. The microcontroller usually outputs 3.3 or 5 volts logical signals that wouldn't be enough to turn on a power semiconductor device. The gate driver ensures that the EGBTs and MOSFETs are being switched with an appropriate voltage level around 20 volts or so. It is also able to give a feedback voltage value about the measured phase current values to the microcontroller. Practically, this measured voltage has a 2.5 volt offset when it is interpreted in a 5 volt scale to be able to express both positive and negative current values as well. The base software's purpose is to handle these low architecture level measured signals with an appropriate conversation logic. The literature is referring to this software level as Hall function or hardware abstraction layer function. For an example, let's say that we are measuring 2.5 volts from the current sensor. In a 5-volt scale, this would exactly mean 0 amps of current throughout the motor windings because of the offset voltage included. The hardware abstraction layer shall handle this conversion and only forward the 0 measured current value to the function software component that is containing the FOC algorithm. For an appropriate motor control software, we shall measure the battery and other low-level voltages as well. In the later slides, you are going to see the reason why they are mandatory to measure. During this slide, we are going to dive into the whole functions to see how the developed function software based on MATLAB Simulink is going to be integrated with other software components in real-time embedded system applications. You can see a block diagram which is representing the different software and hardware layers starting from the inverter as well as CPU and ending with the application software layer. The hardware interfaces forward information about the relevant measured physical quantities usually associated with voltage measurement. Such hardware interface could be the output of a differential amplifier, which could be responsible for the current sensing mechanism, for example. The measured voltage level in this case is proportional to the actual phase current value, so based on this correlation, the hardware abstraction layer can calculate the actual value of the measured physical signal. So, the application layer only receives such measured signals that are already representing an actual physical signal value. The main goal of the whole functions is to ensure that the application software layer is portable between several different hardware configurations. Effectively, the application layer has no clue what kind of hardware is computing the necessary operations needed for the motor control algorithm. This is the interesting part of it as well, that once we have developed the working Simulink model and generated code from it, the rest is up to the whole layer to make sure that the function software receives the correct signal values. In the snapshot, you can see a few examples of already existing Hall functions. The first one is responsible for converting the measured voltage signal to an actual phase current value, where the reference voltage for the ADC converters are 3.3 volts, and the obtained resolution is the 2 to the power of 12 bit. As I have mentioned before, these measured voltage signals shall include an offset voltage level, which is half of the ADC reference voltage value to represent positive as well as negative phase current values. The output of this whole function is a pointer where the struct is being defined with the members of phase A, phase B, and phase C. The next whole function is responsible for converting the actual battery voltage level to an exact value, which can be directly interpreted by the application software layer. You can see that the ADC registers are being read each time the whole function is being called. These whole function calls occur every time the application layer is calculating the needed reference voltage values to the PMSM motor as part of the FOC algorithm. Based on this short overview on the whole functions, I hope that you will be able to place the application software within an embedded software environment. If you have any questions, please don't hesitate to ask. I will try my best to answer them according to my best knowledge. The next step toward understanding the upcoming part transformation better is to clarify how the electric angle of the rotor pole-flux is actually measured in practice. Usually, the manufacturer of the PMSM motor installs a permanent magnet to the back of the rotor's axis for contactless angle measurement. This contactless angle measurement is often carried out by using a so-called GMR or giant magnetoresistance elements. The resistance of these elements are changing based on the magnetic field strength. The basic measurement architecture of such GMR elements is a simple H-bridge connection where the output voltage is interpreted between the two voltage divider. Later, we are going to have a brief look to an existing psychosine encoder datasheet, which is utilizing the aforementioned GMR elements in an H-bridge configuration. In practice, two main encoder types are being used for the field-oriented control algorithm. The first one is the so-called ABI, which is an incremental encoder, and the second one is the so-called sine-cosine encoder. The incremental encoder outputs small angle increments one after another with a certain resolution value that can be calibrated in case of a more sophisticated integrated circuit. The typical resolution value of such encoders are 2 to the power of 12 increments interpreted for a whole mechanical turn of the rotor. From this information, we can calculate the mechanical angle resolution interpreted for an increment step of the encoder signal. Usually, the angular information is being forwarded to the function software by a PWM value as an output of the encoder integrated circuit, which means that the mechanical rotor angle is being interpreted between 0 and 100%. It is worth to mention that the angular information can be channeled via several communication formats, but the main sensing principle is remaining the same using the previously mentioned JMR elements. The sine-cosine encoder, as its name suggests, outputs a sine and a cosine signal from which the actual angle of the motor can be calculated by using an inverse tangent function. In the next step of this course, we are going to assume that the FOC control algorithm receives the angular information by a sine-cosine encoder. We are going to dive into the details of such an absolute encoder by implementing the datasheet of the TLE 5009 IC. Last but not least, I would like to emphasize how important is it to measure the actual rotor angle precisely when FOC is being considered. Based on my previous experience, I can tell that an average angle offset of 5 degrees between the actual and the measured electrical angle of the rotor pole-flux is going to dramatically reduce the effective torque output power of the PMSM motor, not to mention that it may never rotate at all with such an angle error.